Today, we'll be going back to the fundamentals to explore the very language of uncertainty, which is random variables and distributions. These concepts are the bedrock of statistics, machine learning, and quantitative finance. They are how we take the messy, random chaos of the real world and describe it with the elegant logic of mathematics. By the end of this video, you will understand what they are, see the most common types, and witness a kind of statistical magic with the central limit theorem, which we discussed in many videos earlier. So, what exactly is a random variable? It's simply a rule that assigns a numerical value to every possible outcome of a random experiment. It's a bridge from a real world event, like flipping a coin, to a number we can actually do math with. So let us think of it as a vending machine for numbers. You press the button, that's your random experiment, and you don't know exactly what will come out. But you know it will be a number from its set of possible items. The random variable is the machine itself. First, we have discrete random variables. This can only take on distinct countable values. Think about the result of a dice roll. It can be 1, 2, 3, 4, 5, or 6, but it can never be 2.5. So these type of results symbolize a discrete random variable. Now let's look at a continuous random variable. These can take on any value within a given range. Think of a person's exact height. It can be 180 centimeters, 180.1 centimeters, or even 180.112 centimeters. The possibilities are infinite. Now, a probability distribution simply tells us the probability of each possible outcome. For discrete variables, we use something called a probability mass function, or a PMF, which is just the fancy name for a list of outcomes and their chances. Let's look at a couple of famous discrete distributions in a notebook. First up, the binomial distribution. The binomial models the number of successes in a fixed number of trials. Think of it as flipping a coin 10 times and counting the number of hits. Here, we will simulate that. And there is the binomial model's probability mass function. As you'd expect, the most likely outcome is 5 hits, and the probability of getting 0 or 10 hits is very low. Each bar represents the exact probability of that number of successes. Next, we have the Poisson distribution. This models the number of events happening in a fixed interval. A classical example is the number of emails you receive in an hour. Here, we have set the average rate to 5 emails per hour. Now, after running this snippet, we can see that the probability mass function shows that while the average is 5, there's a decent chance of getting 3, 4, 6, or 7 emails, but a very low chance of getting 12. For continuous variables, things are a bit different. The probability of landing on any single exact value is 0. So we use a probability density function, or a PDF. With the probability density function, it's the area under the curve between 2 points that gives us the probability. The most famous continuous distribution is the normal distribution, also known as the bell curve. It describes countless natural phenomena, like the distribution of heights in a population. So this code snippet demonstrates a standard normal distribution. A standard normal distribution is a normal distribution with mean 0 and sigma 1. Sigma is the standard deviation of the distribution. So the output of this code shows the classic bell curve of the normal distribution. It describes the countless natural phenomena. Most values are clustered around the average, and extreme values are rare. Now, another important distribution is the exponential distribution. This models the time between events. Think of how long you have to wait for the next bus to arrive. So, this distribution models something like that. So, this code snippet demonstrates the PDF of an exponential distribution. So, we put the rate of events per unit time as 0.5, and the PDF will turn out as this. As you can see, short waiting times are very likely, while long waiting times are increasingly rare. Now, all these distributions are unique, but there's a powerful theorem that unites them. This theorem is called the central limit theorem. The central limit theorem states that no matter what your original population distribution looks like, if you take many random samples and calculate the mean of each sample, the distribution of those sample means will always tend to look like a normal distribution. So, we can call it the great equalizer. It's like a magical funnel. You can pour in data of any shape, and whatever comes out is a perfect predictable bell curve. So let's prove this. We're going to start with a very non-normal population, which is our skewed exponential distribution. Then our code will take 10,000 random samples, each with 50 data points, and we'll calculate the mean of each one here. So let's run this code. The one on the left, we have our original very skewed population. But on the right, the histogram of a sample means forms a beautifully symmetric bell curve. This is the central limit theorem in action, and it's the reason the normal distribution is so incredibly important in statistics. So from simple conflips to the very foundation of statistical inference, random variables and distributions gives us the language to describe and model uncertainty. They are the essential building blocks that allows us to find the predictable patterns in the heart of randomness.